It's something we do dozens of times a day without a second thought, visiting a website. It just feels instant, almost like magic. But behind that screen, there's this incredible, invisible journey happening, one that literally crosses the globe in milliseconds. So let's pull back the curtain and see how that journey really works.
Okay, so picture this. You type in a web address, you hit enter, and poof, the website is there. But that one single click, it kicks off this unbelievably complex high-speed chain of events. So what is actually going on in that tiny slice of time?
Before we get into the nuts and bolts, just take a second to appreciate this. Your request might be flying through undersea cables, bouncing between data centers, and navigating a dozen different networks to find a computer thousands of miles away. And then it gets a response and brings it all the way back to your screen, faster than you can blink. It's a seriously stunning feat of engineering. So, first things first, the very first challenge is that your computer needs to find the exact computer somewhere on planet Earth that hosts the website you want. It's kind of like trying to find one specific house in a city that has billions and billions of addresses.
And here's the fundamental problem, right? You and I, we use memorable names like google.com. But computers, they don't speak English. They speak in numbers, specifically IP addresses. So the big question is, how on earth does your browser translate the name you typed into a number that it can actually understand and use? Well, the solution is this really clever thing called the Domain Name System, or DNS for short. The best way to think of it is as the internet's giant universal address book. Its one job, and its only job, is to look up the name you give it and hand back the correct numerical IP address. That's it. And this whole system is built for one thing: pure speed. See, before it goes searching the entire internet, your computer is smart. It checks its own short-term memory, the cache, to see if you visited that site recently. It checks the browser's memory, then the operating system's, then your router's. The key here is that it only does a full, fresh lookup if it absolutely has to, and that saves precious milliseconds every single time.
Okay, so now we have the address. What's next? Well, we need to open up a line of communication. But the internet isn't like a direct phone call. Oh no. It's way more like sending a bunch of postcards through a super chaotic global postal system and just hoping they all get there.
And this is a huge, huge challenge. Your requests gets broken down into these little tiny pieces of data called packets. And any one of these packets can get lost, they can show up in the wrong order, or they can even get messed up along the way. So how do we possibly build a reliable conversation on top of such an unreliable system? We solve it with this beautiful layered system of rules or protocols called the TCP/IP stack. It's a brilliant design because it separates all the different jobs. Each layer has exactly one thing to worry about. The network layer just handles the physical stuff, like Wi-Fi or cables. The internet layer is the navigator, routing data across the globe. The transport layer is quality control. It makes sure everything arrives safe and sound. And then finally, the application layer gets to decide what we're actually sending, like our request for a web page. Now, to make sure that delivery is reliable, that transport layer uses a protocol called TCP. And it all starts with this really elegant three-step process called a handshake. It's basically a very polite introduction. Your computer says, "Hey, I'd like to talk." The server says, "Hello back, I'm ready to listen," and your computer confirms, "Awesome, got it." And just like that, the connection is established and guaranteed to be reliable.
But wait a minute, we also need security, right? So right on top of that TCP connection, another handshake happens. This one's called the TLS handshake. This is the crucial step that verifies you're talking to the real server and not some imposter. It then encrypts your entire conversation, which is what turns HTTP into that secure HTTPS with the little lock icon you see in your browser. All right, let's recap. We've got the address, we've got a secure, reliable connection. Now, and only now, can your browser finally ask for the web page itself. And what does that big, important request actually look like? Well, you might be surprised. It's something as simple as this. This is a real HTTP request. It's just plain text. Your browser is literally just saying, "Get me the main page," that's what the slash means, "from the server at google.com. That's all there is to it. It's the digital version of asking for the front page. And this really shows you the fundamental rhythm of the entire web. It's just a simple conversation. Your browser sends a request, and the server sends back a response.
That response includes a status code, like the famous 200 OK, and of course, all the code that's needed to actually build the page on your screen. Which brings us to the final, and let's be honest, the most visual part of this whole journey. The server sent back this big bundle of code. So how does your browser turn that into the interactive web page that you can actually see and use? Think of your browser as a construction worker. First, it reads the HTML file to build the basic structure. That's the skeleton of the page. Then it uses the CSS file to apply all the colors, the fonts, and the layouts. Those are the clothes. And finally, it runs the JavaScript code to add all the interactivity, like animations or pop-up menus. Those are the actions. Now, that whole incredibly intricate process we just walked through, that happened just for you in a fraction of a second. But what's really mind-boggling is that it's also happening for millions of other people at the exact same time. So how on earth does a service like Google actually handle that kind of load? Well, the answer isn't one giant supercomputer. It's thousands of them, all spread across data centers all over the world. When you make a request, you're not talking to a single machine. You're talking to a massive, coordinated fleet of computers. And all of this is made possible by some amazing technologies built for massive scale. You've got global load balancers that act like traffic cops, instantly sending your requests to the least busy server. You have content delivery networks, or CDNs, which are like local warehouses that store copies of images and videos physically closer to you so they load faster. The whole system is designed with one goal in mind: no single point of failure. You know, this architecture is never standing still. It's always evolving. While TCP is incredibly reliable, that polite handshake we talked about adds milliseconds of delay. So newer protocols like QUIC, which is what powers HTTP/3, they challenge that old design. They combine steps to make the connection faster. It's a classic engineering trade-off, really, balancing that rock-solid reliability with our endless demand for more speed. So there you have it. From a simple name you type in a box to a fully rendered web page, it's a journey through caches and address books, through handshakes and layers of protocol, all happening in an instant. This complex dance repeats for every single link you click, every tab you open. It really makes you wonder, as we demand ever more speed and more security, what will the next evolution of this invisible journey even look like?